right, guys, so 10.6 says polar equations of conics, vocab and theorems. We are starting with the vocabulary of number 1, polar coordinate representation of conics. Let D denote a fixed line called the directrix. I know in the parabola we use the directrix with our graphing. Now we don't normally use the directrix to graph our circles or our ellipses and hyperbola, in which we're not studying this year. Let F be the focus. Let E be a positive number. Called eccentricity. Okay, so I'm introducing to you guys a new number called E, which is called the eccentricity. A conic is a set of points. Let's call it P in the plane. Oops, I got to the in the plane, such that the ratio of the distance from F, which is the focus, to P, which is any point on the circle, on the parabola, on the ellipse, on the what are we not studying this year? Hyperbola, okay? Any P. To the distance from D, which is the directrix, to P equals E. In a little bit, I'm going to make this a lot simpler for you guys to understand. Here we go. That is, a conic is called a collection of points P, for which and this is when I talk about the distance, okay? The distance from from F to P divided by the distance from the directrix to that same point. It's equaling to the value of E. Now, what is the shape? It's based on the value of E, okay? If E equals to 1, then it is a parabola. If E is less than 1, then it's an ellipse. Okay, an ellipse is very similar to a circle, okay, and in a little bit we'll kind of look to see how they are related. Now, what we don't study this year, which I'm going to put a star, is if E is bigger than 1, then your conic, it's a hyperbola. So conic, I'm going to spell it out here. It's a hyperbola. All right. So now let's look at this really quickly. Now, this eccentricity value, guys, this is just a very baby step. We're not going to be using it a lot. We're not going to use it in a lot of application, but I do need to introduce you guys to this value for our polar equation, okay? It's useful in a lot of fields, especially astronomy. So let's talk about this value of E. Okay, so E is in the simplest term, it's the ratio. A ratio means it's a division problem, okay? And it's the ratio between the distance from the focus, so look at this focus right here, okay, to any point. So let's pick, this is your point right here, point. And since we're talking about a parabola, we're using this pink curve here, it's a parabola. So the distance from the focus to a point, divide that from that same exact point to your directrix. If it equals 1, then we have a shape of a parabola. Now, if it's less than 1, so let's say this is your point, okay? So from the focus to the point, take that and then divide that same point, here's the point, to your eccentricity, or in this case, the directrix. If it's less than 1, then it's going to give you an ellipse. And in a little bit, I'm going to talk to you guys why we don't do a circle on here, okay? Now, what we don't study is when it's bigger than 1. So from that same focus, we don't study it, but I still have one right here, the hyperbola in purple. So let's say that I'm going to pick this as your point on the hyperbola. Okay. From the focus to that point, take that distance, divided by that same point to the directrix. If it's more than 1, then you know it's going to be hyperbola. So that's what it means in terms of the eccentricity. Now, before we talked about these two shapes right here, okay, let's define the eccentricity, E of the ellipse below, so we can go back up and talk about those two shapes right there. So eccentricity, which is the value of E of an ellipse, and in years past we were also defining it for the hyperbola, just not this year, okay? For an ellipse, E is going to equal to C divided by A. And what is C? C is the distance from the center to one focus, right? One focus. Okay. Then A is distance from the center to one vertex. Okay. Now let's tie the same exact E value to the definition from above. Remember, the E definition from above is distance from that one focus point to a point P divided by the distance from the directrix to that same point P, which is now, for the ellipse only, it's C divided by A. Now let's look at the two pictures here and see what it means, okay? Here's the center. Here is your C value. Here is your A value. So C from that picture, it's a lot shorter than A. So we know that's going to be less than 1. So we know that's going to be an ellipse. But what happens is when the gap of C gets closer, and not the gap, the distance of C gets closer to the distance of A, it's making your ellipse more narrow, right? So here's C, and then here's A. So the closer the value of E to 1, the narrower your ellipse is going to be. Now eventually it's so narrow that it's at the very edge. So look at this purple right here. So if it's at the very edge, E equal to 1, and E equal to 1, then that makes it a parabola. Now what happens when the two foci, okay, when it's 0, meaning that the distance from the center to the foci is 0. I mean, there's no focus at all, right? The focus moves closer and closer to the center, so the distance here is 0. Well, if you have C equal to 0, why am I making that? Okay, if C equals to 0 divided by whatever A value is the center to the edge? Well, as you know, the center to the edge is called the radius when it's talking about the circle. So this is the radius. Well, it doesn't really matter what a is in the denominator. 0 divided by any number is going to be 0. So when your eccentricity value is 0, it's going to give you a circle. So that's why we don't really talk about the e value for circle, okay? Now let's go and finish up this definition. So when you have, earlier we had this definition from above, just like that. We can do some algebra manipulation to get a few more definitions out of it, okay? So the first thing we can do is we can cross multiply. So if we cross multiply, we have e times the distance from that directrix to a point P. That should give us the distance from the focus to P. Now we can also solve for the distance from the directrix to P. So the distance from the directrix to P, if we again do some algebra manipulation, we should have our distance from the focus to the point divided by our e value. That just those two equations derived from algebra manipulation. Okay, let's go on and do the theorem. Polar equations of conic. The focus here, if you can see this, it's always at the pole. And your e value that's used in here, it's going to represent the eccentricity. Okay. Equation number 1. If UCR equals e times p divided by 1 minus e cosine of theta. This is your polar equation of a conic. With the focus at, whoops, that's all together, at the pole, and directrix is going to be perpendicular to the polar axis, at a distance, let's call it P to the left of the pole. Okay. So next equation, R equals E times P divided by 1 plus E cosine of theta. Now, the first few words will be the same. It's still going to say polar equation of a conic with the focus at the pole. So I'm not going to write that down on each box. So I'm just going to do dot, whoops, I didn't mean to have a highlighter there. We're going to do dot, 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 and we will continue with the directrix, okay? Directrix is still perpendicular to the polar axis. Okay, so that part's still the same for this. At a P, distance to the right of the pole because it's a positive cosine. Okay. Next, we are going to take care of the sign. R equals E times P divided by 1 plus E sine of theta. And again, we're going to do dot, 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 and we'll start with the directrix. Directrix is going to be parallel to the polar axis. At P distance. Since this is a positive sign, it's going to be P distance above the pole. And then our last polar equation is going to be E P divided by 1 minus E times sine of theta. Now it's going to be super similar to the one right above it. The directrix for this one, since it's sine, it's still going to be parallel to the polar axis at P distance below, below the pole. All right, now let's just review a little bit what the E value mean. If we have an E value equals to 1, that's going to give you a conic of a parabola. Okay, so the conic is a parabola, and the axis of symmetry is perpendicular to the directrix. Let me just go get a different color pen to get the next E value. Next is going to be E is less than 1, and we talked about this quite a bit. The conic is it's not a parabola, it's definitely an ellipse. Okay, so it's an ellipse. And we have major axis is perpendicular to the directrix. Now we really don't study hyperbola, but just for filling it in, okay, this is going to be a hyperbola. And because this year we don't really study hyperbola, so we don't need to fill out the rest. Okay, so I know that when we were studying parabolas, we graph the directrix all the time. Here are some pictures of where the directrix might be for your ellipse and your hyperbola, which we don't study this year. For the ellipse, technically, guys, we have two. One's here and one's on the other side of the major axis. Okay. If we were to study hyperbola, we also have two. One's at the end of each vertex. So this one's one, and here's another one. So that's where the directrix technically are. Okay. And again, let's just recap. Okay. The directrix is perpendicular to the axis of symmetry of a parabola and does not touch the parabola. A parabola is a set of all points in a plane which are an equal distance away from a given point, which is focus, and given line, which is directrix. And the eccentricity, which is the E value, if you look at our picture here, is going to be from the focus to a given point, and then from that same given point to the directrix. If it equals to 1, then that is going to be your parabola. This is just kind of tying up all of the first two definitions that we just got done writing down. Okay. Now, an ellipse is going to be, we have two directrix, so we just have to pick one and two full side. So the directrices are two parallel lines on the outside of an ellipse perpendicular to the major axis. So in essence, it's going to be perpendicular, it's going to be parallel to the minor axis, okay? All right, so we use one of the directrix to define an ellipse. The ratio of the distance to the nearer focus, okay, so pick a focus and pick a point. So the ratio of the distance to the near focus to the distance to the near directrix equals a constant that is less than 1. This ratio is called E, which is eccentricity. So if we pick the right focus, okay, because you want to pick the closer of the two, and let's say this is our point, let's pick this is closer. Okay. So from the focus to here, that should be the same distance from here to here. Okay. I'm sorry, not the same, less than. So let's say this is L1, this is L2. If it's less than 1, if we divide L1 over L2, and if it's less than 1, then it's going to give us an ellipse.